Okay, you've been working for 2 chapters now on this data understanding phase. It began back here in visualization when you learned Tableau and got started with making charts and graphs. So here in the bivariate visualization section, we talked about data types, introduced you to the Tableau environment. If you were new to it, you could go through this getting started video. Then I walked you through this video with the bike buyers data. And if you remember, the idea was we were making charts and looking for differences between bars if the independent variable is categorical, or we're looking for trends in scatter plots if the independent variable was numeric. But the idea and purpose of this was to take every feature, or in other words, every independent variable, and chart it against the dependent variable, or the label. In purchase bikes, that was the purchase bike column indicating whether or not the customer purchased a bike. So we went through every possible other independent variable to see if we could find any differences. Differences are good because they show us that there's a relationship, that people in this case, North America, purchase less than those in the Pacific. And by knowing that, that tells us that the variable region is a good source of explanation for whether or not someone will purchase a bike. If they're in North America, they're less likely. If they're in the Pacific, they're more likely. Anyway, so we went through and there was some background on trend lines and slope. And then we shifted over to this statistics chapter. The idea here was to then test and further examine each of those visualizations we came up with and see if the relationship between that independent variable and that dependent variable was statistically significant, or understand it further. So we learned about how to make correlation matrices to see just how related these variables were. Then we learned how to use ANOVAs to test whether that relationship between a categorical variable and a numeric variable was significant. Then we learned also about t-tests that let us drill down to examine the difference between 2 and only 2 categorical values, like male and female, or one level of education versus another level of education, to see if those were significantly different. What you need to do now, or what you might still be struggling to understand, is how to put all the charts together with these bivariate statistical tests together to generate an output for the data understanding phase. And what does that output look like? Well, if you recall, back in the very beginning of chapter 6, we reviewed 4 outputs. There's 4 different reports that come out of the data understanding phase. Data collection report, which is where we get the data from. The description report, which is a high-level description of summary statistics. And there's better ways of generating this report than what we've learned in Tableau. So I'm going to show you an example of these reports, but I'm not going to force you to generate this quite yet. But then we have the data exploration report, which is the one that I want you to create for your checkpoint now. This is what you've been learning how to create. It includes all the charts and graphs and the bivariate statistics. And I keep using that term bivariate because our focus at this point is only on pairs of variables. In other words, I'm always looking at the dependent variable, or the label, and one independent variable, or one feature at a time, and that feature's relationship with the label. Then there's also this data quality report, which kind of goes hand in hand with this data description report. And I'm going to save this one. I'm not going to make you generate this one yet either, because you'll learn a tool in later chapters that makes this really easy. So let's talk about and focus on the data exploration report. Here's what I've done to try and help you out. If you're watching this video, then you're at this point at 7.6, or the data exploration report section. And I've got this example here of the data understanding outputs. So this is more than what you'll need to generate for your checkpoint here. You're just going to make the data exploration report, but I wanted to show you a document that includes all of those 4 reports together in one and show you what that might look like. Now, I'm not going to give you a standard template or format that I want you to use. Really, you'll have some standard that your company wants to settle on, or that you'll decide that you'll use for all of your reports across all phases of the CRISP methodology. But here's one example. So I've got my collection, description, exploration report, and quality report. So I'm doing this for the bike buyers data, and I'm not doing it for every single variable. I just want to keep it simple for now. So your collection report is just simply an example of where your data has come from. Here I just put the details for the server. I put even the table name, which fields that I pulled. I also mentioned what other data sets we looked at and considered for this data mining project, and gave it brief explanation maybe, or a source they can go to explain why we didn't use those data sets after all. But again, that's just an example of a simple version of what goes in that report. Next one, the data description report. There are all these simple things like the count, the number of fields, unique values in each field. So marital status has only 2 values. Income has 16 possible values because it's rounded to the nearest 10,000. Then I've got the min and max values for each of these fields. And then here's a bunch of other variables: variance, standard deviation, skews, kurtosis. There's an easy way to generate this all at once, and I don't want you to have to worry about it yet at this phase, so I'm not forcing you to do the data description report in your checkpoint. However, this is also a good place to put the correlation matrix that you did learn how to create in this phase. So I think I would like you to come up with the correlation matrix, although I wouldn't mind it if you stick this in your data exploration report, even though normally I would see it here in the description report. But I think it would be good for you to go ahead and generate this since we did it in the chapter. Here's the data exploration report. What I've got is a subsection for each potential label. Notice back up in my table of contents, I've got marital status, education, age, and then the summary right here. So here for marital status, I'm going to go through and say, here's my explanation of what marital status is, because bikes, and my theoretical explanation, and albeit it's a very, very simple one, of what I expect this variable to do. So because the bikes offered at ABC Bike Shop are primarily designed for fill in the blank, we expect to see that married customers purchase bikes at a higher rate than single customers. Furthermore, and I just go through and I explain why I think that married customers are going to buy more than single customers. Now, this is not always necessary, formally stating a hypothesis. Also, where is this going to come from? It could be a variety of places. It could be the data analyst. It could be their interviews with the business side or people who work in this domain to get what they want. But then what you're going to have next, anyway, is some sort of chart or visualization. So in this case, because marital status is a categorical variable, it's a very simple bar chart. And I get that the text is really small here. This says single and married. So single people, I made a chart showing the average purchase bike numeric for single versus married customers. And you can see that on average, the opposite was true. Single people bought bikes at a higher rate than married people. So you learn how to make these charts in Chapter 6. However, I'm not done there. I don't know if the difference between these is statistically significant. What tests would you use here? Well, you learned about correlations. That's one thing you could show, and that would come from your correlation matrix right here. You could show that marital status and purchased bike numeric has a correlation of negative 0.11. So as people shift from, and this backs up what you're seeing here in the chart, as people shift from single, which is marked as a 0, to married, marked as a 1, the likelihood of purchasing a bike goes down. Hence, this negative sign here on the correlation for marital status against purchased bike numeric. So that backs up what we're seeing here, the difference between these two bars. Now, the reason why we're able to come up with a correlation coefficient here is because we came up with a numeric version of marital status. Instead of having it be married or single, we changed it to 0 or 1. Otherwise, if it was text, we wouldn't be able to come up with a correlation coefficient. So a correlation coefficient is possible here only because it's a bivariate. There's only 2 values of this category. But you'll notice here I didn't mention a correlation coefficient. What I said instead was, all right, however, despite our expectations, a simple bar chart depicting the average shows that it's the reverse of our hypothesis. To verify this finding, we performed a simple t-test. So t-test is one of the statistical analyses you learned that lets us compare the differences in a numeric variable, which is purchase bike numeric, across 2 categories of a categorical variable. So we looked at marital status and the 2 categories it has, and we compared differences in purchase bike numeric across those 2 categories. So using Excel, using the Excel t-test formula, and assuming 2 tails, because the reason why I went with 2 tails here is because I had a theory, but my theory was wrong. And in practice, my data showed that single people were higher than married people. So I decided to use a 2-tailed test to be more exploratory. And equal variances, this data produces a p-value of this right here. So I'm using my bivariate statistics to validate or back up or support what I'm seeing here in the charts, or to further explain it. So then I say, therefore, we conclude that marital status is a good candidate variable to use in the modeling phase to explain bike purchases. Why is it a good candidate variable? It's because there is a statistically significant difference in the height of these two bars. So therefore we say, let's include this variable when it comes time for the modeling phase to explain who purchases a bike. However, we do not have a good explanation yet for why single customers purchase at a higher rate than married. So this is where the detail goes for each variable. And I went through and did the same thing now for education. I said, okay, I think that greater levels of education will result in greater bike purchases. Here's my chart. My chart says, yeah, you're right sometimes, but not all the time. Bachelor's is the highest rate of purchased bikes. Oh, it looks like I made this a count and I should have made it an average. Anyway, let's assume this is an average rate of purchases. Anyway, but graduate degree is smaller than bachelor's. So it's not perfectly linear. Partial high school is the smallest. Yes, high school goes up, and then partial college goes up, and then bachelor's, but then graduate goes down. So I can't say that that's always true. So what I do, how do I test differences in categorical variables where I have more than two values? That's what the purpose of the ANOVA was for that you learned. The ANOVA gives us an F statistic and a p-value which says, yes, across all 5 values, there is a statistically significant difference. And it doesn't care if the bars are going up or down as education increases. It also doesn't tell me if one individual level is different from another individual level. It just says across all 5, there is a significant difference. So I say, okay, we learned a few things. Yes, education is a good explanation of purchase bike numeric, and we should include it in the modeling phase. However, because it rises and declines as education increases, a rank-ordered version of education, like we used in the data set when we created the correlation matrix up here. This was education rank-ordered that gave us these coefficients. And I said, however, a rank-ordered version may not be the best, should not be used. We recommend treating education as independent categories. And you'll learn later in the modeling phase how we do that. So again, there may be a variety of explanations, and here's our ideas behind why this turned out that way. So one more example. You've learned where to use a t-test up here for marital status. You've learned where to use an ANOVA and what charts we use in each. Now let's show you one more, age. As people get older, they have more disposable income and are more likely to be able to purchase non-essential items like recreational bikes. Therefore, here's my hypothesis. As customers get older, they become more likely to purchase a bike. For this one, I made 4 charts. Why? Because I went further than just making a single straight trend line. So because age is numeric, I get scatter plots. Scatter plots are when we have 2 numeric variables. Purchase bike numeric, clearly numeric, and then age is numeric. So I plotted made a scatter plot and added a trend line. And then both Excel and Tableau give you this formula and an R-squared value. Now, if you use Tableau, it also gives you a p-value to tell you if the angle of this line is statistically significant, meaning that that line is steep enough that you can say that there's a relationship between the X variable age and the Y variable purchase bike numeric. So if you used Tableau, you would have had a p-value too, and you could further use that in your justification here. But R-squared is good enough. What I did here is I said, okay, a straight line gives us an R-squared of 0.01. A logarithmic line got worse. A natural log line, this is a polynomial line with a squared term. It got better. And a polynomial line with a cubed term got even higher, got to 0.03 for R-squared. So I'm going to say that this is the best way to model the relationship between age and purchase bike numeric. So I write up my conclusion here. Once again, our hypothesis was wrong. As customers get older, they're actually less likely to purchase our bikes, as indicated here by the straight line. See, the straight line goes down. But then I say, however, an analysis of the trend line reveals that this relationship is clearly not linear. In fact, the best description of the relationship between these 2 lines is a polynomial term, both a squared and a cubed, indicating that there's a positive relationship from age 20 to age 38. Right here it goes up. Then 38 to 75 it goes down. Then 75 on up it goes up again. Although it should be noted we don't have a lot of data for customers that are 75 plus. So our interpretation of these results, I give my explanation. There it is. So that's what I'm doing. I'm going through and I'm using my t-tests my ANOVAs, my trend lines, and then even my correlation matrix to explain the relationship between each independent variable and the dependent variable. And then if you want to, I think this helps, you can come up with a little summary table here that says, all right, for each variable, here's my Pearson correlation. If I was able to calculate one, if it was relevant, here's the test I used to calculate to look at the relationship between this variable and the dependent variable. Here's my result. And I might summarize here those that seem to be the most promising to affect the dependent variable. So that's it for the data exploration report. Down here in the data quality report, this one's very simple because I didn't have any missing data. So I just basically said no missing data. But that's it for my outputs of the data understanding phase. Now in the checkpoint, I want you to focus on and create just the data exploration report.